Ja, det höll faktiskt 87 minuter.
1,5 timmar. Då är vi folk trötta.
Ja, så nu är vi live.
Nästa gång får vi köra med kabel. Det är
vi göra. Skicka ut en som du gjorde tidigare. Har de hållit sig? Skickade du något?
Jag hittade hela.
Hur många timmar hade vi på senaste? Var det 55 också?
57.
Ja, det gick ner till 53 ett tag där. Men det...
Nu är vi live.
Ja.
Live igen.
Ja, så det är bara att köra på.
Nej.
Jaha.
Ska vi ge folk en chans att koppla upp sig?
Okej, live igen. Okej, så det är vi upp här. Vi ser om de slår upp här inne. Jag tittar.
Men du vill kanske skicka ut den nya länken?
Till mina föräldrar skulle jag vilja göra det.
Facebook, gör det.
Eftersom att de inte får vara här.
Gå och titta nu.
Det är du och jag.
Jag tittar. 4. Okej, nu börjar det. Plocka in.
Aha, det var i titelfältet.
Svensk så att det är också någonting.
Man ska ha en reservlänk som är förberedd.
Okej, nu börjar den plocka in Magnus och kommer tillbaka. 5 på arm.
Okej, så nu kör vi igen. Medan det funkar.
Ja, 1 sekund. Mamma, pappa. Kissa in sin
Mamma och pappa någonstans.
ny link till restaurans. De är hemma.
Okej, Eva. Kör på.
55 tum. Okay, Nikki. We were talking about single mode VCSELs and fabrication. And,
the challenges you
yes. So
you think or you see trying to get the VCSELs operate Singapore.
yes. So in order to get the VCSELs operating single mode, a big part is the material design. So the epitaxial growth, all of these layers need to be designed properly. So that happens even before I start fabricating. And that per se is a challenge, because we would like to play around with moving the oxides, having them depending on how you design the neighboring layers around these layers that oxidize. They can be have a very high oxidation rate or a slower one, which will give them a more tapered look. You can place them, you can design the optical field so that you can place them in nodes of the optical field, these oxide apertures, or you can place them slightly on the side of these field nodes, because if you place the oxides in a field node that's where the optical field is low, you will have less impact and less. You will have weaker guiding, which will give you a more single mode design. So we would like to play around with these things, test them, but since they are embedded in the material design, it's very hard to do iterations. What I can do during fabrication is I can, of course, find an optimum oxide aperture size, and I could play around with mode filters, which I have. For instance, we tried to or we have made successfully with the 850, we have etched a surface relief, a little ditch for those of you who like that expression better, in the top of the VCSEL. So it's a circular hole, it's etched more in the center, in a circle in the center. And there, their reflectivity is optimum for the conditions you want to lace. But on the sides where we have less edge, you will have a worse, for those modes, a worse reflectivity, and thus it will not be prone to lace at the high probability. So you will, by doing that, you can force the VCSEL to become single mode, even though you have a larger oxide aperture. So that we've done a little bit, and also, I think most of the design to make it single mode happens before you actually fabricate it.
Right. But as you fabricate, you have variation in the process, for instance.
Yes.
And that will impact the ability of a particular design to deliver.
Yes.
What do you think was more critical based on your experience?
During entire fabrication?
Yes, during processing.
I would actually say, like a minute ago, I said how easy it is to do oxidation. But oxidation isn't completely easy. You want to be able to control what kind of compounds you are making, and like the oxide, what gases or what materials you actually have in your oxide. When you oxidize, they will change in size. The material will introduce strain to the device. The temperature is critical. You should not go too high. You cannot go too low. It needs to be stable. So oxidation, and you can also, when you oxidize, you don't only subject the very high aluminium content layers to the water vapor. Your entire chip is subjected to this process, and you can get, if the edge on the other parts of the chip isn't protective enough of the surfaces, you can get cracks in your entire chip, and various things can happen.
Right. So now you mentioned the oxidation, of course, is one of the key process steps there. And if I understood correctly, you were around 4 micron diameter with oxide aperture?
Yes, for our single mode design.
Right. So how critical is that dimension? What if one is 10% wrong from 4 micron? Are you falling off a cliff?
10%, no
it's just
problem.
say 10% worse than the optic.
10% is no problem. There's not a lot of change in the statics or dynamics if you change the oxide aperture by 10%. What I see is, so say that this material D2, it becomes single mode at 4 microns. A 3.5 micron device will still perform. It would be hard to distinguish them. It will have a slightly higher resistance. But underneath, say 3 microns, when they become 2.5, we can't really make them 2, 2.5, 2.8, and 3. Then you start to see that the resistance goes up significantly, like exponentially, almost. And I've also seen when I try these very, very small ones in large transmission, they are not as reliable as others. So the VCSELs I publish, they have been undergoing extensive measurements and have been tested for hours and hours and hours and hours. We've done some reliability measurements, but none that have targeted reliability. However, when the oxide aperture size was as small as 2.5, they tended to actually degrade quite quickly. So I think at some point, when you oxidize too far, you will have reliability issues, probably due to the strain and other defects. I've also seen that the oxides of those VCSELs, it could be basically dependent on the amount of time they have been oxidized. Maybe if the MESA was smaller and you made the oxide aperture 2.5 microns, it would be fine because the time to oxidize would be shorter. But when you had oxidized for a very long time, the oxides would be uneven. You could have defects very close to the center of the device, and that would cause problems with reliability.
Right. So you mentioned resistance going up very rapidly as the aperture gets slightly smaller. So is this as expected? I would say, scaling just with the area of the aperture, or do you see that resistance?
So the resistance should be proportional to the mode. I think the mode volume somehow. I don't have the I'm a bit tense also, so I don't have the equations in my head. But when you reduce the oxide aperture size, it's not only the area. You reduce a circular area, so yes. The resistance.
So when you, I'm sure you got VCSELs with a slightly wrong aperture compared to what you were targeting. Was your feeling that they kind of scales with the area of the aperture, or
yes.
did it more rapid change than?
At a certain point, it's more rapid, but I think that depends on other issues, such as almost closing the active region. So until they are 2.5 microns, it scales with the we made calculations on that, and it scales with the area, injection area.
Right. So that's as expected, so to say.
Yes.
Right. Thanks. So now let's look at multi-mode versus single mode and some other parameters. How, for instance, relative intensity noise, GR, bandwidth of the VCSEL. Can you try to give some kind of general trends for these parameters from what you have seen, and if that was as expected, or if you have seen something surprising in your experimental results? If we take, for instance, how ring changes with adjusting the size of the aperture and other changes you need to make to get a VCSEL single mode. Which one gets a lower ring in the end at the operating point, and was that behavior as you were expecting, or were you surprised by it?
So RIN, something that I can't say I was surprised, maybe, but RIN can be affected by optical feedback. But if you measure RIN on a single mode VCSEL, like in order to measure it, you need to couple the output to something, and that something might easily generate the feedback. So if you have any reflection or anything, you will get the VCSEL output back into your VCSEL. And single mode devices can be very sensitive to this. So, and that can definitely be seen in the RIN. And some of the RIN curves I measured, they look like pieces of art. Like someone took a pen, like a paintbrush, and just did threw the paint all over the place, because the VCSEL was being disturbed by optical feedback. So that's not even something, you can't see a pattern in that data.
Right.
So you have to make sure you don't have optical feedback into your laser if it's a single mode laser. Multi-mode VCSELs are a bit, because of the mode competition. In that case, the modes contribute to each other, and they are not as sensitive to optical feedback as this a single mode VCSEL is. Let's see, I was a little bit surprised at how low bias currents I found the RIN, because when you look at the measurements in hindsight, it's very easy to see the characteristic. We saw the peaking of the RIN at the resonance frequency, and you can see it goes from in the single mode VCSELs, from a very low low frequency RIN up to the resonance peak where we have the most RIN, and then it goes back down again. So that pattern is very clear. But when I started measuring, I was measuring closer to 1 milliamp at devices of the same size as the ones I presented, and I did not see anything, because I had much, like when you develop a stage, you have much more noise in the beginning than after you've established your measurement method. So I could not see this behavior, and I was surprised that the peaking occurred at and that the RIN settled to the noise floor as quickly as it did. That was a surprise to me, but it wasn't a shocking amount, but it was still, so I had trouble finding the actual characteristics of the RIN in the noise
Right. So, but now if you would compare your multi-mode device and the single mode one,
yeah,
and based on the experience you have now, is it a dramatic difference in RIN at the optimum operating point for transmission? So what I have in mind is you need to reach
yes,
where you want to operate on large signal modulation.
So yeah.
Is it a major difference between a single mode and a multi-mode device? If I look at RIN, bandwidth, OMA, I can so optical modulation amplitude,
yes.
jitter, or are they kind of comparable? Of course, in the end they will reach a different distance and have different properties in a way. But at this more basic level, are they fundamentally different, or essentially they are more or less comparable?
So yes, that's
your impression?
a good question. So at 1060, we haven't published any of those results. At 850, we have a publication that shows that the difference between, as we move to a bias current where the RIN has settled, the multi-mode VCSEL will have a 10 to 15 dB higher RIN level. And what I saw with the 1060, when I've measured a few of my multi-mode VCSELs, I saw about the same behavior. So that was not a surprise, and and it's about the same as for 850. The multi-mode VCSELs, because yes, of the many modes, they don't really settle at shot noise level. They settle at a higher level, about 10 to 15 dBs higher compared to single mode VCSELs.
Right, so that's a big difference.
Yes.
So how about bandwidth and optical modulation amplitude you reach with a single mode compared to the multi-mode device?
Yes, so...
now I mean bandwidth of the VCSEL itself, so you would measure back to back.
So that's a tricky question for me, I think, because the multi-mode VCSELs we have are much larger in size than the single mode VCSELs we have.
Sure, but that's right. Yeah, they are multi-mode, they are bigger. Yeah. They are different devices, so to say.
Yes, but we do also have two devices that are differently strong single mode, like higher order mode suppression, and the ones that were less single mode, so more of multi-mode devices at the smaller aperture size. They become single mode at a much smaller aperture size than the second device. Those tended to have, let's see, I need to dig in my memory, slightly higher modulation, like a multi-mode, a larger VCSEL has a smaller modulation bandwidth. But when we measured and compared these two devices, there was a slight benefit in modulation bandwidth for the one that was less prone to single mode behavior. But I can't really say that's a fact because I have to revisit those numbers. But it was a difference if the one design had a modulation bandwidth of 21 gigahertz, the design one had a 23, so it's a 2 gigahertz difference. But between the multi-mode, if we also include the size, multi-mode, single mode, a larger VCSEL will have the smaller, in general, the smaller modulation bandwidth.
Yeah, okay, good. So how about jitter? Do you have any general comment, single mode versus multi-mode on VCSEL? I mean, so to say.
Well, a single mode VCSEL should have stronger gain suppression. So it should have a more damped response. And therefore, the overshoot and ringing should be less with the single mode device than a multi-mode device. And if I look at my experimental data, for instance, in the papers A and B, I said that we measured static and small signal on both single mode and multi-mode, but then I only showed a single mode long transmission results. It's because the multi-mode VCSEL performed slightly worse. It did achieve 40 gigabits per second back to back, but it did not come up to the 50 gigabit per second as the single mode VCSEL did. And the eyes, even at the same speeds, they look. It looks like jitter is a bigger problem with the multi-mode device.
Right. And you understand this based on the fundamental properties.
Yes.
So it's not really a surprise.
No.
Okay. So what do you think one should focus for the future development? Now you brought this. You studied this topic and achieved very good results. What do you think someone should do to push this further? What should one focus on? What are the key elements we should look into?
I would, let's see. So I would love to see more epistructures, similar but with slight variations. It's not maybe a key thing to focus on, but it's something that will happen if more people focus on this type of device. I think the 1060, or it doesn't have to be 1060, it could be 1030, it could be 1050. But I think that range of VCSELs has a good use in future data centers. So I do believe people should focus on those, and then we will see more EPIs in this on this wavelength. So that will be interesting to see. But focusing then maybe on trying to achieve single mode, because I do think we're moving towards more single mode optical interconnect. So it could be with multimode fiber, universal fiber, or single mode fiber, but at least a single mode VCSEL. So I think one should focus on trying to integrate that into the design, as well as maybe trying to come up with new ways to filter out the fundamental mode, or promote fundamental emission, fundamental mode emission. Because if, for instance, if you use a mode filter on top of, I personally, with my materials that I have now, I would love to make a larger oxide aperture, maybe a 6 micron size, so larger than the 4 micron that was single mode by the oxide aperture. So I would like to have that. It would have like resistance less than 100 ohms, maybe 80 ohms or so, which is beneficial. And then I would want to make a mode filter on top of it in order to make it single mode. That would give us a single mode VCSEL with low resistance and higher power, and that higher power could be used for PAM4, for instance. And I think that would be a very powerful device.
Right. So is now discussing the mode filtering. So is there any idea to say select the next of the mode instead of the fundamental? Still single mode, but not the fundamental in the VCSEL.
That's the research that I think is pretty exciting. The more creative paths. I think we need to do more research in looking at what's the benefit of the other modes, because they do have a different spatial distribution. Maybe you can benefit from this in some way. Maybe you can use it with a special kind of fiber. I don't know enough about it, but I think that we should learn more about it. So.
Sure. Okay, good. So now, if we look at the transmission experiments you made, you tried 2 levels, so no return to 0 essentially, and then
yes,
tried PAM4 the 4 level. Did you consider any other format, at least theoretically, or maybe even tried in the lab?
Yes.
And do you have a general comment related on which modulation format you believe to be more suitable? And now I would split this in two different cases. Say you only want to go 50 meters in one case, and say you want to go 1 kilometer in the other case.
Yes. I think for 50 meters, I would definitely consider PAM4, the 4-level modulation format, just because you increase the symbol rate by such a degree from just going from 2 levels to 4. And for 50 meters, we've already proven that we can do good, we have good results from 100 meters already with PAM4. There are other modulation formats as well, as you can add complexity there in various forms. But I do think the simplicity of the PAM4 is what is going to be used in standards today and also for the next 10 years maybe. Commercialized products are of course slower than the research, so maybe we'll see research into other modulation formats, but I still think PAM4 will due to the simplicity compared to increased more advanced modulation formats, PAM4 has its benefits. And with only 50 meters, the power will be enough for 4 levels, so I don't think you need to restrict yourself to 2 levels. You can make sure to have a well-suited response of the VCSEL in order to accommodate for the 4 levels. So yeah, PAM4 definitely. And then for 1 kilometer, not so sure there. Maybe we have your first question. If we tried something else, we tried duo binary modulation, which has, with some tweaks, it has 3 levels, 2 eye openings. And we saw some good results from that, but it's not very common in standards, at least. But that's a potential modulation format for the 1 kilometer case, where you might not be able to squeeze in 4 levels. But with 1060, if we could make that device I was just describing, it would be interesting to see if we can do PAM4 at 1 kilometer and 2. But without that device, I would say Juno binary or PAM2 so far at 1 or 2 kilometers, due to the need of. It's not that many dBs though. But
So-
the chromatic dispersion also you still have some chromatic dispersion. You can't you can reduce the effects of chromatic dispersion by using a totally single mode system, but you will always have the chromatic dispersion effects there with the fiber. So due to that, I think you would need binary or dual binary.
Right. So yes, now it's true that the electrical domain has kind of set the standard at the moment. In any case, they settled for the 4 level, and unless you use some more complex electronics in the module, the preference would be to just transfer that to the optical domain. But I believe that maybe dual binary has more potential than, let's say, dispersions is limiting the bandwidth. But you measured chip. And I think that was a very interesting measurement, and a little bit unusual at this wavelength.
Yes.
What's your view on this? What is going to be the impact of chirp in a link of, say, about 1 to 2 kilometers based on pixels? Is this going maybe to be some kind of fundamental limitation at some point, or you think there are ways to deal with chirp, maybe in the pixel design or somewhere else in the link?
Oh, well, yes. So what we saw when we investigated the chirp was that we got ice cues because the combination of the sign of the negative chromatic dispersion and the sign of the chirp, like the direction of the chirp, those in combination at like on the rise. During the rise time at that transient, because of that combination, you would experience, and the chirp was different at the beginning and the end of the transition. So you would experience that the rise time would be longer after transmission, and the fall time was shorter. So you got an ice skewing because of the chirp and the dispersion. So it can be a limiting factor, and let's see, how can you mitigate or take advantage of that? Maybe.
Is there anything we could do with the design of the VCSEL to at least reduce the impact of this effect?
Well, it all has to do with the dynamics and the chirp, the frequency fluctuations in the VCSEL has to do with the small refractive index changes that happen as the signal settles to a level, to a power level. So it all has to do with the dynamics and the coupling between photons and electrons. So I would assume there is a way to mitigate the chirp, but I am at the time not aware of how to do that actually. So, but because it's all coupled to the fundamental behavior of the VCSEL, it should be possible to design to lower the effects of chirp.
Yes, so maybe this is a very interesting topic for someone else to.
Yeah. Yes, and since we saw the big effect on the skewing, I mean, maybe the skewing could benefit transmission, and you could get a clearer eye, or yeah, it could be interesting.
Good. Thank you very much.
Thank you.
So, Nikki, you are happy with what you heard so far?
Yes, thank you very much. It was very, very good, very interesting discussion.
Yes, I'm also very happy about the discussion. It was very nice to hear your questions.
Do we have the committee online? Have you been able to follow the discussion?
Yes.
We have Professor Karsten Even from Technical University of Denmark. Would you like to start?
I can do that. Yeah. Can you hear me?
Yes.
All right. Good. So, yeah, to start out with, I'd like to congratulate you on your work. on producing some of the best high-speed VCSELs in the world. Continuing that work from your group. I also appreciate very much the careful and detailed measurements and analysis that you have presented, and I think it's a well-written thesis. I do have some scientific criticism, which is related to missing details to reproduce the work. So, I mean, if I were to copy your work, I would miss some details. Most importantly, details of the epitaxy and the process details.
Yes.
So this is probably on purpose, but I still want to mention that. Anyway, so some detailed questions. So you have these two designs where one of them has moved the oxide aperture to 17 nanometers to the active region, is what you write.
Yes.
So when I first saw that, I was thinking it was the distance to the quantum well, and that got me a bit worried about reliability. Why would that be?
Let's see. It would be. Ooh. Well, I'm thinking. I mean, the cavity needs to have a certain length, but I'm guessing you're thinking about something else than the actual cavity.
Yeah, something process related. So in reality, you don't have 17 nanometers to the quantum well. It's much bigger, as far as I can see.
The quantum wells are in the very center of the active region, and around the active region, we have a region of gallium arsenide, I think, on both sides.
Gallium arsenide phosphide, I guess.
Yes, and then on top of that, we have the mirror. So there's a buffer region, or to make this half lambda cavity.
And why is that important?
It makes that's in order to get the standing wave of the optical field, we want it to be half wavelength long.
Right. That's definitely one thing. But why it's important for reliability? In the old days, I guess, there have been a lot of debate about oxide-confined VCSELs and reliability and so on. What is that debate about?
Well, I guess the oxides introduce strain in probably one direction, while the quantum ones introduce strain in the other. So maybe you would get a skewing that would decrease the reliability.
Strain can do that, but you're doing these tapered apertures, which helps a lot there.
Yes, they are very thin and at the very tip of the taper.
But what is actually going on when you do this oxidation? I mean, the physics of that, the chemistry of that.
Well, not very. Let's see. So you do introduce water vapor and they oxidize the aluminium. It's algas layers, and I think the oxides expand while you do the oxidation. But chemically, what kind of the oxides introduce a capacitance, but I'm not sure what you're grasping at.
Well, I'm basically asking you because you've done a lot of process development work.
Yes.
I guess in terms of time, that has been a huge amount of what you've been doing. So I'm just trying to dig a little bit into how much you actually went into the theory of those processes.
Yeah, the oxidation isn't my high point.
All right. Anyway, there will be some arsenic generated that will diffuse into the nearby areas, and if they go into the quantum well, that would be a problem. But you actually have a barrier, which when you have the first part of your thesis, the introduction part, so you can actually see that, but it's not clear from the papers themselves.
Nice, thank you.
Anyway, one thing that I was thinking about for these single mode VCSELs, I mean, what about the yields? I mean, Nikolai was a little bit into this also, but I mean, when you go from multimode to single mode, does that from a production perspective give you some issues?
Not with the, no, the yield is not different. It's in the cases where I oxidize way too far, like way more than 10% too much, then I see a yield difference. But as long as I'm targeting the between 3.5, 4 microns, and then the yield is the same as for the multimode devices.
Okay, so in practice it's not an issue.
No.
What about? I mean, you have this interesting technique where you adjust the top reflectivity.
Yes.
And so this was not discussed. Is that how is that done in practice? Is that a one iteration or is it many iterations? How do you do this?
It depends. It could be both. Ideally, if you do it in a large-scale fabrication, it's one step. In research, we could do it if we know how far we're gonna etch. We have 1D simulations that give us a relation between the slope efficiency, like when we measure the LIV curve, so the statics of the laser. We get a slope efficiency. I'm just explaining for anyone who doesn't follow, and that slope efficiency can be related to the photon lifetime, and we simulate that in 1D simulations. And so by measuring the slope efficiency, so you fabricate the device, measure the LIV, and then go back down and etch the amount you want to etch according to the simulations. But in the first time we do this, and we haven't tested this material before, we etch first once, maybe different amounts on neighboring VCSELs, or once on the same VCSEL, then again, and then again, and then again, to get several points and to really see where the photon lifetime is at its max and where it's at its lowest point, and the reflectivity as well. They are related.
But the theory actually fits with the experiment.
Yes, the only vague number there is the internal quantum efficiency. That's estimated from curve fitting.
Right, okay.
So that's the most risky parameter. But the trend is the same. So the trend, the max and mins will still occur at the same edge depths, but the internal quantum efficiency will lower or decrease the curves, both the photon lifetime and
yes.
slope efficiency.
Yeah, they are in one of your papers.
Yes.
The curves. All right. Good. Then I also wanted you had something in your slides about you write that since it's a new epitaxy, you need to do a lot of developments, and you had something on your slides. But maybe you could say, I mean, what were the main things you needed to develop going from the 850 to the 1060?
The main thing I had to develop. Let's see. We can. So you on YouTube can't really see all of the slide, but so I write here that we did material simulations, representation, and mask design. So when going from 850 to 1060, I needed to make sure, because the DBRs will be adjusted for 1060, and a DBR is based on the wavelength. So the MESA is taller in a 1060 device than it is in an 850. And also the compositions are a bit different. So I needed to validate the etch rates. I made this simulation that is shown on screen here, at least, is from transfer matrix method, an intensity. So I simulated the reflectivity through, if you look at the material from the top, so you have the entire epitaxial structure and the substrate in the bottom, you will get, if you emit with the laser on top of that, you will get a reflection. And I simulated that using the TMM. So when etching, we can actually in situ follow these curves in order to know how deep we've etched into the epitaxial structure. So those simulations needed to be made. I also needed to develop the mask because the photolithography is very sensitive to, even if it's almost the same material as the 850, the photolithography will not come out the same. So all of those recipe times and developing times need to be adjusted in order to get good patterns in order to then deposit the and etch with a good precision. Let's see. I could actually remove one fabrication step from the process, which was in 850. We don't have as much binary materials in the bottom mirror, if any. So there we use a contact layer in the bottom. We etch first the top mesa to confine the active region and then oxidize. And then we etched a very tall bottom mesa and put the contacts in a contact layer underneath the bottom DVR. But in the 1060, we used intra-cavity contacts, and so that actually simplified fabrication a little bit. Yes, I changed the thickness of the metals in order to use them as I used the top contacts in my case as a mask because we wanted to reduce the mesa size to a much smaller one than we used before. It was 15 microns instead of 20. So I used the metal ring, the top contact, as a hard mask when etching. So I ran some tests and tested that, and then also.
Is that also the reason why you have smaller parasitics in paper C than paper B?
Yes. Yes, it is. I think we'll take those as a highlight, and there's fabrication is including every lithography step. It's about 30 or so different sets. So there's a long way to go.
Yes. All right. I'll leave something for Richard and others also. But just one final question, which is probably difficult. So in paper C, you show a ring curve that goes. So in figure 6.
The alignment.
You have a ring curve that goes below the shot noise.
The ring.
You have ring including shot noise that goes below the shot noise. So that is for the final question. Is that theoretically possible?
I'm guessing you mean this figure.
Yes.
Yes.
Yeah, so here you have ring including shot noise that goes below the shot noise.
No, it's not possible to see. Let's see. Yes, so it goes below the shot noise level, and it depends. Let's see if I can see it again. I shouldn't have put it down. Yes, around the frequencies of 5 gigahertz there.
And in some ranges.
Yeah, I'm gonna think of, so the shot noise level is 4 milliamps. I mean, there is an uncertainty in the measurement, so but I do try to think if there was something that I've missed.
So this is probably an academic question, I would say. Practicalities is probably not so interesting. But what does the shot noise limit actually mean?
Well, the shot noise, so you have the thermal noise limit and the shot noise limit that usually limit your system, and then the shot noise is much lower than the thermal noise limit, and it depends on it's related to the random events during photon generations, I think.
Yes.
So it's both in the VCSEL, and then also on the detector side, you will have this shot noise in the dark current of the photo detector. So there's shot noise coming in from at least 2 sources here, and you can't really measure, like, that noise limit should set a noise floor for what you can measure. So you shouldn't be able to measure a signal below the noise floor, shot noise floor. But I believe that these curves are subject to maybe an error margin that when they reach the shot noise or something similar.
That may very well be true, but it is in fact possible to go below the shot noise.
Really?
If your generation of photons is not random. So this is something that was shown in the 80s that you can do if the current that you send to your laser has very little noise, then the photons you get out of it will also have less noise than the shot noise. Oh. Normally, when you transmit, then it becomes Poisson in the end. But in this case, you actually have a very efficient laser coupled with very low loss to your detector. So in theory, it could actually be true. It might also be in the machine there.
Interesting. Thank you.
Thought it was interesting. That's probably more on the academic side. All right, but I think I'll pass on the word to the next one.
Thank you very much, Kristen.
Thank you.
So thank you. I think we go in distance and closer to us, I guess, is Royal Institute of Technology. Well, it may not be closer.
I think actually we're the closest.
Yeah, you're the closest. So. But
yeah,
national-wise, let's go to the Royal Institute of Technology with Richard Schatz. Are you there? Hello? Richard?
Yes, I'm here.
Do you want to pose some questions to Eva?
Yes. First of all, thank you very much for inviting me here to the evaluation committee. And I want to say to Eva, it was very nice pieces to read. It was nicely disposed and well written, I think.
Thank you.
And also it covers the entire range. I mean, from fabrication, characterization, analysis to system experiments. So it was a pleasure to read it.
Thank you.
Yeah, and I also want to say that I'm impressed by the clean modulation response and RIN measurements you have done at Chalmers. So it's really nice to see that you can measure RIN in these devices with such a good dynamic range.
Yes.
I have 2 topics really to questions on, and will be a little bit more theoretical.
Ooh.
But it's first it's on sharpened dispersion, and the second one will be on relative intensity noise.
Yes.
Yes. So when it comes to sharpened dispersion, if we look at page 20, equation 3.9.
Yes.
Yes. There you have in the first parenthesis, you have the product of C times beta 2.
Yes.
So what is the sign of C and what is the sign of beta 2 in this expression?
Well, for my devices or my fibers, beta 2, well, I would say, let's see, I just had a course on this, so I should know it. Well, I guess they together should have a negative sign, if I'm not mistaken.
Yes.
So
you measured this compression, or you saw this compression.
Yes, I have it in I would say that the beta 2 is negative and the chirp is positive.
Oh, I'm sorry.
It's the other way
it's
around.
Opposite.
But it's mixing it up.
Yes, the D is negative. You're correct. The D is this version, but beta 2 is in fact positive. And C here is negative.
Yes, beta 2 depends on the dispersion. The dispersion is negative because it's the picosecond per nanometer kilometer. So that's the minus 31 of the fiber. And
yes, but beta 2
is related to D by the equation in 310. Yes. So it becomes positive. And the chirp was measured. Where do I have it? Here. And yeah, the chirp, although this C is the theoretical C here is for a Gaussian pulse. So in order, this is a single mode VCSEL, so it's fairly Gaussian, but in order, you can't really derive it from the frequency chirp measurement that I have in this. You have to extract it in a different way. I just want to get it up on screen. This is the chirp measurements that I made. But yes, we did estimate the chirp, and I think we have a number in my paper here somewhere. I think we estimated it to somewhere around there, 2.1.
Yes, and it's sounds so, but it will be negative 2.1.
Yeah, negative 2.1.
So how is this short parameter C related to the alpha parameter of a laser?
Oh, that's a good question. So in my work, we did in paper D, together with Pierluigi De Bernardi in Italy, we made a very long. Or do you mean the alpha parameter of the fiber?
No, of a laser.
Of the laser, yeah, good. Because Pierluigi made simulations of the alpha parameter, and I'm not really, like, he was part of that work mostly, and he has a very extensive model about how to extract the alpha parameter from the gain simulations. And how is it related to chirp? Well, let's see. Alpha is related to the carrier density. And the chirp has to do with the carrier and photon density, the rate equations at least, the coupling between them. So I'm not sure what the relation would be, but I can definitely see that there should be a relation between them.
Yes, I mean, in fact, in theory, if everything is perfect, C is just minus alpha.
Really?
Yes.
C is minus alpha.
So if you
that's too easy.
you probably have an alpha parameter around 2.2 in your laser or in your laser material, but that would be interesting to see. I mean, it's because the chart is really the FM response, the frequency deviation. At when we say that the chart is C is equal minus alpha, we assume you only have a transient chart, which is not. And then we come in. There is also a adiabatic chart. What is that? And what is the?
You mean the difference between transient chirp and adiabatic chirp?
Yes.
As far as I understand it, the adiabatic chirp is the chirp that, because the chirp parameter is that one is derived from, like, you need a pulse in order to see that transient chirp and derive the chirp parameter. And that's transient chirp. But then the adiabatic chirp is the chirp that happens during, like, when you in the signal here in the picture on the screen, the adiabatic chirp would be the chirp between transients, as far as I understand it.
Yes, it's correct. And what physical mechanisms can cause this adiabatic chirp?
Well, during this period between, like, the signal is turned on, and that causes this rapid rise time overshoot ringing. And during the adiabatic chirp, you still have, or this period where you might see adiabatic chirp, you still have the ringing from the relaxation oscillations during that time period. So I guess it's related to that.
Yeah, maybe a little bit, but not mainly. Mainly it's due to very slow effects. I mean, more slower effects. So what slow effect can affect the wavelength of a laser? I mean, apart from that the carrier density suddenly fluctuates. But what can give it
I'm thinking about spontaneous emission, maybe. Slow effects. Let's see. No, I actually can't think of it. My brain is empty.
Yeah. There can also be large fast effects giving adiabatic chirp. You can say adiabatic chirp is the chirp which is more or less proportional to the intensity, whereas the transient chirp is proportional to the derivative of intensity. So it's the slower effects and mainly spatial hole burning, and also gain compression.
Oh, yes.
This.
Oh, yes. Okay.
Yeah. But
gain compression.
Then I wonder if you would compare a multi-mode fiber and a single mode fiber at 1060 nanometer.
Yeah.
And you would write how the reach depend on the bit rate. How would the curve look like? Is it possible to sketch them on the board behind you or something like that?
The reach, sorry, your audio went down a little bit.
So we reach as a function of bit rate.
The reach is a function of bit rates.
Yes, so you have bit rate on the x-axis.
And reach here.
Yeah. Could you turn off your screen sharing so I can see your other picture bigger? Yes.
Yes. Let's see if I can find this stuff. I think I need to.
I guess one could also draw on that on the PowerPoint.
Is it possible?
I think so, but I don't know if it works for the audience.
I can take up.
It's also possible if you can draw it on computer. Yes.
Let's unshare and see how big it is. Maybe.
Yes, unshare. Let's unshare, and then I think it will be big enough.
Yeah, I will just find the settings here. Stop share. There's your face. How do I exit?
Yeah, maybe I can see, well, it's difficult.
We can do this.
Stäng av. Stäng av.
Nej, det kanske går att se.
You can pin the video, then it's full size.
Oh, good. Thank you. Yes, I see you now.
It should be here.
Thank you.
But you can't reach up there,
so you have
to lower it.
But yeah, you can see me in this camera.
Yes.
Oh, okay, in that one, yes.
So,
Oh, yeah, good. Now I see.
so I can make it larger too.
Yes, yeah. And then we use sort of logarithmic axis. I mean, we rate there and reach on the y-axis.
Bitrate reach, you wanted a multi-mode fiber and a single mode fiber.
Yes.
And let's see, speed, reach, let's see. Well, SMF, here we have 0. So, and this is back to back. I need to just figure out what I have here. So back to back, if I have with my 1060 nanometer systems.
Yes, with your 1060. So back to back, you can write on the x-axis, I think so.
So I guess we only tried 2 kilometers.
Yes. Yes. No, there is bit rate. Sorry.
Oh,
so,
bit rate. Sorry. That's
see,
I'm not used to this.
Yes.
So there, 2 kilometers, 1 kilometer.
Yes.
And let's see, we did.
And 1 gigabit per second and 10 gigabit per second, maybe, or something like that on the x-axis.
Yeah. Yeah. 10 and.
Or
did you say 1 and 10?
1. Yeah.
You want the logarithmic one?
Yes. Yes.
Yes.
So maybe 1 and 10 on the y-axis also. I mean, or yeah, on the y-axis also the logarithmics. So 1 and 10.
That makes more sense because at 10 we can reach further than so I'm guessing with an SM we did get far away here. I see one. We have done this, so we've been up here and in this region and
yeah. So I'm more interested how fast, what before that point, and how fast does it fall? I mean, in the for a multi-mode fiber and the single-mode fiber. I mean, the single-mode fiber, which one is going the farthest distance, first of all?
The single-mode fiber should go the furthest distance.
Yes. And how fast does it fall after you reach that distance?
Well,
I mean, how if you increase the bit rate?
Well, I've never done it in this scale before, so it's very unintuitive for me. But let's see. So I guess it would be. This is so difficult.
I'm sorry. But before you come to the dispersion limit, at some bit rate you come to the dispersion limit.
Yeah.
What happens with the curve then? Is it completely flat, or I mean, is the reach constant, or does it decrease, or?
So before.
No, well, we can say at 1 kilometer, for instance, up to 1 kilometer for single-mode fiber. What happens then? Then you have no problems with dispersion.
Yeah.
Yes. So when you increase the bit rate up to 1 gigabit per second, does anything happen then with the reach?
Oh, okay. So at these very okay. So what we do have is I need to just have this as a in my inner eye, because at very, 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 very low speeds it looks very much like this, and it doesn't matter much for the like a very, very low speeds that even at like 2 kilometers, if we're here somewhere, it will be fairly, let's see, if we're at the same reach, it would be fairly constant.
Yes.
Yes. So I'm just gonna do something like this.
Yes, it will decrease a little bit because you need the same, the noise increases because the bandwidth of your system increases a little bit. So it will slope a little, but hardly noticeable.
I guess
so,
if you
so at higher speeds, it's a little bit more difficult since you need higher bandwidth of your receiver, so you get more noise.
Yeah.
Then for the single fiber, what happens when you reach the dispersion limit?
So
and it drops, and how fast does it drop?
When I reach the dispersion limit, it starts to drop quite rapidly, I think, from experimental experience. I reach, because I can see a consistency in my measurements from 30 to 40, and then maybe 45, and then like it's, if I'm at 1 kilometer, then it just starts rushing down.
Yes.
So I guess reach at those, I mean, it would start to, this number is quite annoying, but I guess here somewhere it would start to like fall down.
And how fast is it? 10 dB per decade or 20 dB per decade?
Ah, okay.
Do you think?
Oh yeah.
For single mode fiber.
For single mode fiber. Okay. Oh, those units are, I haven't used those in a while.
Yeah, but it doesn't scale in proportional or inversely proportional to a bit rate, or does it scale proportional to a bit rate square, inversely proportional to bit rate square?
Okay, let's see. I would say the square.
Yes, and why is that?
Oh. Well, this feels like I should know actually. Let's see. There's this 4-bit. Schematic description, bit rate. I'm not. No, I can't dig that information out.
I know. Okay, it doesn't matter. But you know, when you have higher speed, you get smaller distance between the bits. Of course, at higher speed, you have less tolerance to broadening, but also the broadening increases because the spectrum increases. So the problems with dispersion becomes worse. So you both get, I mean, higher, smaller distance for smaller tolerance for broadening, but also larger broadening. So that's why it goes like square.
Okay.
But for a single multimode fiber, you don't have that. Instead, you go not so far, but then it falls just bound over a bit rate. So it falls less steeply, but but you can't go as far.
I'm not sure where to put this in height.
You can put it at the same level,
At the same level.
But, yes, and then it will fall slower after you reach the distortion limit. But yes, not so. It goes well. It starts to fall earlier.
Yeah, that's what I'm thinking. But I'm thinking, I mean, you can't come these distances. So you're thinking it would go.
Yes, something like that. But even earlier, I would guess.
Yeah, I don't really like the numbers. I would
Thank
like
you very
to
much.
do
I'm
this.
sorry about it, but thank you very much.
Because
So
the numbers keep.
let's go on to RIN instead.
Okay.
Yes, and then I want to focus on equation V12 you have.
Yeah. 312.
Yes.
Let's see. Yes, the RIN. Here I say that.
Maybe we can push it on screen. Do you have?
Yes, I think or no, I don't have my. Well, I did post it.
In fact, I have it here in front of me, so maybe I can share it.
Like on your video?
Yes. Let's see if I can. There's screen here. And you see it. So share. Okay. Do you see my screen or your thesis here?
Whoa.
You probably have to increase the size.
Oh, you.
Okay.
Yeah, take that down a notch.
So, okay, now?
You could have gone to the zoom feature on the menu.
Okay. Okay. You mean the size like this? Okay. And I will just zoom it in. So.
312.
Yes.
Next one.
No, it can be very large. I put it to 200. Let's see. And then I will try to just. No. Oh, it's stupid. This. Sorry, I have problems with my controls here. So let's see here if I can zoom it in. So yes, so I'm talking about this equation here.
Yes.
Yes. First of all, here, where does the amplifier noise come in? Is that included in the RIN, or is it in the thermal noise? Doesn't seem to be included in thermal noise. So
it's included in the total noise power. So he's talking about that first sigma total is a noise power that includes the entire system. But actually, you asked about the detector of the amplifier.
Yes.
So actually, in this equation, you don't want the signal power. I think this one is. You don't want to have the signal power of the amplifier included in your because you want to know the RIN of the VCSEL. So when I measure this, I measure a total signal power that includes the thermal noise. That's why we have to remove the thermal noise. It includes the shot noise as well. It includes the RIN, and so that's what we want to have. But when I measure, I also have the amplifier noise, and I have to. I guess it's included in this sigma total because I have to. Before I measure the RIN, I characterize my amplifier and detector.
Yes, So I think you include it in thermal noise, don't you? I mean, you subtract it from your measurement.
No, the thermal noise. Well, it's like this. So, so the sigma total is the entire setup, everything. So the VCSEL is turned on, it's biased. So you have the VCSEL RIN, and you have the amp, and you have the everything included here.
Yes.
And then the sigma thermal is the everything again. Oh, it's included in both. And then
exactly.
Yes.
So in sigma thermal, I think 314 here, you should include the noise figure of your system, shouldn't it? I mean, because you really subtract the noise. You don't calculate the thermal noise when you do. You subtract you measure the thermal noise, and that includes your amplifier noise, I would guess.
That is true. Let's see.
Yes.
Yes. And so I subtract, so I measure the S21 of the amp and everything, and then I subtract it from the total, from all of it. And yes, it should include the noise figure, but I don't think we stated it in the equation. I'm not sure if that's...
No, it's missing in the equation 314. I think you should have a noise figure there.
Yeah.
However, there are other problems with 312, which are more serious, I think. If you do a dimensional analysis of it, so if please just do a dimensional analysis of all terms there, if you can do it.
Oh, okay. And so we have the noise powers here, and then...
Yes. What is the noise powers? What is the dimension of them if you look in 313, for instance? What is the dimension?
Well, the dimension.
Yes. I mean, Q is Coulomb. R times P0 is current, isn't it? And delta F is charge.
The responsivity is amperes per watt, right? P is watts. I think it's amperes per watt. And hertz, which is per second.
Yes.
And ampere seconds, watts, coulombs. Let's see, those disappear. I don't remember the code. Watt second, ampere, or is it ampere second?
Ampere is coulomb per second, so you can. I think the unit should be ampere squared, isn't it? It's the current variance you are different there.
Yeah, ampere squared. That's true.
Yeah. Yes.
Yes.
So all these sigmas, also sigma short, and sigma put and sigma pH, they have the same unit. It's ampere squared.
Yeah. What did we say? We said ampere per watts for the responsivity, and then watts squared. That's ampere squared, and then we have an omega here, which is lika varje gånger is volt per ampere or omega. I'm not sure if omega is SI units. Ampere. So I guess we get amperes per watts.
Yes, and it seems strange, isn't it?
Did I miss something?
Yeah, I can say the problems here. There are several problems. First of all, you have defined sigma shot in another way than you did in the paper. So a stigma shot here, as you define it here, should be above the fraction bar. It should not be on the side of a fraction bar.
Oh, it's because it's defined differently, yes.
Yes, and the RL in the denominator should not be there. There should be delta F instead. Because this should be, it should be per watt, per
I think we have an errata.
It should be a unit V of RIN. So there are several mistakes in this formula that you maybe want to.
So maybe one mistake made me do several mistakes.
Yeah,
that's not good.
Well, I think they are independent.
Yeah.
You have even in the paper, I think, but and that is that you say that it's hours, and then you know you want RIN to be per hertz.
Yes, that's true.
But in the paper it's correct with this shock noise as you have written it, because there you have defined the shock noise in another way.
Yes.
Yeah.
That's why I was confused. Okay.
Yeah.
So
yeah,
I
it's always good to make a sort of dimensional analysis when you have a formula. Because I understand you have measured this, and what you have measured is correct. It's just when you put up the formula.
Yes. I appreciate that you found this.
yeah, you're very welcome. So yes, otherwise I have no questions more than what your plans are after this. Will you stay at Chalmers or?
I'm hoping to be able to continue work with VCSELs or transceivers for high speed, maybe disaggregated links, but I'm hoping to do that in the US, where there's plenty of companies pushing the state of the art. So I'm looking for a job.
Oh, I see. Yeah. So maybe you go to 8 labs or something like that. So thank you very much, Eva. So that's all my questions. Yeah.
Thank you.
Thank you, Richard.
That was tricky, but it was fun.
Yeah, that was good. A bit of excitement here. Do we have Lena Wosinska online from Chalmers?
Yes, I'm here.
Okay, great.
So first of all, thank you, Eva, for a nice presentation, and I'm delighted to be part of the grading committee for your thesis. My research, one of my research areas is also optical interconnect in data centers. So in this sense, kind of similar as yours, but my focus is more on architecture design and optimization, and also resource allocation. So I don't focus that much on component technology like you do. So my questions will be more related to some, we will be not that much, let's say, theoretical as Rickard's, so you can relax now. Okay, so in figure 1.2, and also on your 5th slide, you showed some architectures of also topologies and architectures.
Yes, in the introduction. I hope you all on YouTube, but that you actually went ahead and downloaded my thesis, because I sent the link to it. Yes, page 1 and 2. No, 3. Figure 1, 2.
Slide 5 in your presentation, but maybe you can go to
I can go to the presentation, of course. Sorry.
There are, in fact, two different, slightly different architectures, but...
Did you mean the spine leaf?
No, but maybe you don't need to show. Just I would like to ask you if it was any reason that you selected this to show, or...
the spine leaf? Or the factory?
Yeah, if it is a certain reason that you show, because there are plenty of architectures that are proposed in different places, including our group.
This is actually something I would like to ask you, because I was reading a bunch about the fat tree topologies, and they have a long history in data center networks. And with history, I don't necessarily mean time, but I mean there are many iterations of the fat tree topology. And they use advanced mathematical structures in order to come up with these topologies. And this spine leaf topology is fairly a new iteration of the fat tree, where they have a very heavy there are lots and lots of connections between these servers that are the spine servers and the leaf servers, and then you have the or switches, I mean, not servers. And then the servers are connected in clusters and also are heavily connected in between each other. And the reason why I chose to show this one is partly because this topology allows for switches that are, they don't need to be very complex or large or have very high switch capacity. You can, since you can have many more of them and have many connections, they will not have, as I understand it, as high as a load at the same time. So you can have reduced requirements on these switches, but have more of them. And this, the reason then, partly that, because that reduces, could reduce cost if you don't have to have these really advanced switches. And then also this topology requires a huge amount of connections, optical interconnections in between these levels, and a limiting factor there is the reach of a single optical interconnect. Like if you don't have long enough optical interconnects, this architecture won't scale at a certain point. But I wanted to ask you if this is actually a relevant topology to show, because I tried to look into it, but it's a big research area in itself.
Well, the advantages and disadvantages of all proposals for architectures, of course. For this topology that you mentioned, I think the main advantage is that there is a high survivability or reliability of connections, because then if something goes down, then you can use another path, and there is a variety of choices. But my question is also, you consider that the switches are optical also. So you consider the transparent connections between servers or between top of the racks or between pods?
Right now I'm considering them to be electrical, because that's what I believe is available. I do think optical in this type of topology and optical switching would be immensely beneficial. So that would be, yes, that's a potential of this architecture.
Assume transparent interconnects between servers and or tops of the rack.
Right.
They try to eliminate this aggregation tier in the data center. So from top of the rack you go to the core switch directly.
Mm-hmm.
So this is the main trend, and also it saves a lot of energy, because in addition, if you have electronic switches in the aggregation tier, it will take a lot of energy, and you would need to have a lot of interfaces and so on.
Okay.
So this was my first question, and the second one is so your since you assume electronic switches, so you assume the switches on packet base by packet basis, right? Mm-hmm. So this is what the optical switches will not do.
Yeah.
My other question is if you have some thought about free space interconnects, optical free space interconnects, in particular in data centers. I think it is kind of interesting approach, but how your VCSELs would then fit to this? Do you think it would be interesting for interesting application for VCSELs?
Wow, I'm not really sure how the free space interconnects would function. I guess, is that for very short distances, or?
It can be. I mean, that doesn't need to be very short, but maybe not on the order of tens of kilometers. But I think hundreds of meters, 1 kilometer should go.
All right. Well, the 1060 VCSELs that I have fabricated have beam divergence that would not allow for that communication. I guess with the correcting optics, you can do a lot, but I'm not sure what the ideal light source would be. You would certainly want something that's highly directive. I've never actually considered free space. Is that something that is an oncoming trend, or is it something that has been used before?
Does it save on cabling? I mean, as you shown, or no, in fact, I think the opponent shown in his slides.
Yes, in the introduction.
And it can be a solution to minimize or to limit the cabling. And I have seen some presentations, I mean, on the conferences where they suggest to apply free space optics.
I guess, in these data centers, we need a lot of different technologies in order that compensate each other. You can't go with one technology for all distances, all purposes, all lengths. So you need to have probably a combination between, and the free space optics seems to be one of them. I guess they use a different light source, but I wouldn't be able to give my I'm not sure how these systems what the transmitter looks like, so I don't dare to say what kind of light source should be used.
I was asking because at this conference that I mentioned, they referred to advantage that they experimental, they use some different lasers, but they complained that they don't have access to VCSELs. They would be better.
Yeah, I can imagine that these transceivers can be made quite bulky, and that by now, like today, maybe like you can do it with a bunch of. What I want to say is that I think they can be made with a various, like many different kinds of light sources. You can add optics and add things in order to make it work. But what is the most ideal light source? As I said, I think it would be something that can be highly directional without as many correcting. It should probably also have the energy efficiency in mind. And VCSELs are energy efficient, so I guess it's a good option. So And if they are complaining that they want VCSELs, then probably VCSELs are good. But
actually,
I'm gonna pick up an article on that and see how those transceivers are built or transmitters are built. Yes.
Yeah. So another, I mean, it's more like a comment because you mentioned that you also applied forward error corrections and DSP, but regarding latencies, I mean, in the data centers interconnects, latency is very key problem.
Yes.
So I think it would not allow for this kind of.
In my publications, we haven't used forward error correction in any of the results I have published. We have used equalization and we have used pulse shaping. And pulse shaping is, as you say, something that might not be, it's not optimum in a data center. I'm not sure if, I did write a little bit about it in the thesis, but I don't remember if it adds latency, but I do know it adds to power consumption and bulkiness of the transceivers. And equalization can be made fairly simple with few taps. You don't have to have it both in the transceiver and transmitter and receiver. You can try to minimize equalization. But yes, I do think that we should aim to have as little tricks, so to speak, going on and make the circuits as simple as possible. Just due to the power consumption, latency, congestion, like the actual space that the transceivers require. So that's why I try to make my transmission measurements in such a way without using equalization or DSP of any kind, or analog either, signal processing.
Also, I mean, you refer to, I mean, as a motivation for your work, you refer to increasing capacity, I mean, requirement for the capacity in the big data centers.
Yes.
But in my understanding, it will be, in the future, it will be a bit relaxed because of the latency issue. So instead of have a few big data centers, it may be better to have a number of small data centers. So
yes, that's why I think actually the switch that I recommended you to take a look at, I don't know if they're a brilliant company, but I do think their marketing is brilliant. And they are focusing, they have 4 sites in the US, and their biggest one is actually, as you say, several, it's not the biggest data centers in the world, but they are still hyperscale data centers. But they connect them, they have, each data center might then have better latency requirements, and then they can connect them and make a bigger network out of several fairly huge data centers.
And also to have smaller data centers close to the users. This is, I mean, to reduce the latency of
oh, you mean between the user and data center? Okay.
Yeah, of course, there is a trade-off for energy efficiency, because if you have big data centers, it's more energy efficient than to have a lot of small data centers. But
okay. Yes. I'm not sure how. I think that's a future development that we will see. But I don't think. I think we will still have a few decades, 1 or 2, with the developing these large data centers for sustainability, because if you just do the helicopter perspective, usually when you have a new technology or a new industry, first everyone has not first, but in the beginning, everyone has like small, like businesses have their own. In the data center, we've been having lots of small data centers, like server rooms, at many companies over the world. And as they develop, they start to conform. And usually businesses do conform after a while. And then after they have conformed, and a new technological breakthrough can make the technology more like ooze into our daily life, like in a more integrated way. So the technology in the future will become more integrated with our lives. And as you say, maybe the first step towards that is smaller data centers closer to the end user.
It's already happening. I mean, there are almost, I mean, now for the 5G, let's say, technologies, they are talking about data center in all base stations, let's say so.
Yes, but what if in 50 years everyone had a small base station in between their walls? So maybe that will happen. So that's what I mean. That's happening already, but I mean that it will become even more integrated, so that we don't even see it. That's. I'm sorry for being a bit up there in the air, but that's how I would like to see it.
Yeah. So my final question is then the more from my curiosity. In figure 4.2, you present refractive index and optical intensity in the longitudinal direction close to the active region.
Yes.
So basically, the oxide apertures are formed by oxidation, where aluminium-rich layers oxidize faster, right?
Yes.
But here I'm not very clear if, because this aluminium would also change the refractive index, in my understanding.
Yes.
But the refractive index here is kind of the same, while the oxide aperture have different length. So
yes, it's a 2% difference in aluminium content. So the refractive index is pretty much the same, but the 4 secondary oxide apertures have 96% aluminium, and the 2 primary have 98% aluminium content. So the difference in refractive index is very small compared to the oxidation rate. Yes.
But simply, it is not this. I mean, the figure didn't show this small difference, so it's like.
Well, 98 and 96% can be. This is not the. These are on the screen. I'm not sharing it with you, but here we see 4 secondary oxides, and the primary actually are oxidized somewhere far into the left. And this is what happens along the edge, because these layers have 90% aluminium in them. You can see a slight tiny difference in refractive index. It's probably like 0.5 millimeter or less, but I can see a slight difference. But it's a good question, because it's interesting how sensitive the oxidation rate is to the aluminium content.
Okay, so this was my final question. Thank you very much.
Thank you very much, Lena. Yeah. So Does anyone else in the committee have any questions that you forgot to ask? Our opponent might have something still. So is the committee and the grading, is the grading committee and the opponent happy so far with the answers? Then we will go to the audience here to see if we have any questions from the few people in the room. Do we have any questions here?
Can I ask?
Yeah.
Sorry but I fatigue you with my question. But anyway, I'm not very familiar in your topic, but my investigation is connected with multi-core fibers transmission.
Yes.
Fiber.
Oh.
So I'm very interested. Is it some future with VCSEL, which is connected to multi-core fiber?
Yes.
Okay.
So it's a very good question. I think maybe I can just paint it in Paint or something.
We can see the board. That's fine.
Yeah, you can.
Use the board as
Okay, I'll use the board. At least the people at home can see how I move my arm. So maybe they can follow. So what I use is a VCSEL with a single core. So you can do many things to aggregate the capacity from this. So as I said before, you can add several links next to each other like this. So standard is to have four fibers next to each other, and then also in each center you can add multiple wavelengths, lambda 1, lambda 2, and you can do that here as well. Up to today I spoke about 8 wavelengths, for instance, as an example. And another way of doing this parallel lines, so this takes up space, right? And transceivers will be bigger. So what you can do instead is to do what you are researching, is to have a different kind of fiber that has, I don't know how many cores you're using, but you should be maybe using 6.
I investigate 3-core fiber.
Ooh, 3-core
right
fiber.
now.
That sounds cool, but I've seen some that have 6. I haven't seen 3, but that's probably a reason behind that. But then you can transmit, instead of having 6, or in your case 3 fibers next to each other, you can transmit them in one core. And also the difference then, here we have a regular VCSEL, like a separate VCSEL structure. From the top, looks like I usually have a contact, and then you can probe it. Sometimes you make the pads square, and you add signal and ground to it. But these can be made in VCSEL arrays, where you have an area where you probe, and then you can position the VCSELs next to each other and control them on the same chip, so they take much less space. I mean, this distance here would then be matching that there. So you can drive all of the VCSELs using the same pads, at least I think. I'm not sure. Anyways, they take up less space. So it's a benefit. You don't need to have parallel, and then you can also still use several wavelengths in each core and have a high capacity, a very high capacity.
Okay, thank you.
Yes.
So we have an online question here by Stavros Giannakopoulos. Is that from the group?
He's from Microwave Electronics Group.
Okay.
Not from Photonics.
So the question is, are there other areas, applications of these VCSELs besides fiber optical communication?
Well, you can use them for sensing applications. I measured very low line widths on my VCSELs. And the low line, a reduced line width is good for applications where you need a very small spectral width. So in sensing, you can also use VCSELs to in applications where you have atomic clocks. Is there anything else? There are several applications, but those are the two I can come up with at the moment.
And then there's a question by Åsa Haglund. There are two tweets here. The detuning on the VCSELs affects most of its performance, such as modulation speed and energy efficiency, that are important in your work. I didn't find any information about the tuning of the VCSELs in your papers.
No.
What is the detuning in your devices? Is there any room for improvement by optimization this further?
Yeah, there's room for improvement. The detuning that Åsa speaks of is measure between the photoluminescence peak of the active region. So the wavelength of which the active region will have a luminescence peak, and the DBRs have a different frequent wavelength where they have a resonance. Let's see, it's easier. So the difference between let's see, I think, so this is the gain of the VCSEL, and this gain peak is related to and a little bit estimated by a photoluminescence peak. So this is wavelength here. So at a certain wavelength, you will have a peak in the gain of the VCSEL, and then the photoluminescence peak. They can't measure the gain peak when they fabricate the material, so they measure something called the photoluminescence peak instead, which is a peak that when they use I guess a spectrometer, they grow the active region on a substrate, and they look at where, and they inject carriers, I think, and look at what wavelength. They scan the wavelength to see where they have a peak. So this peak is 1045 roughly, or was designed to be 1045 in our devices, and it should correspond roughly to the gain peak. And then we have the mirrors, which, well, that's a bit exaggerated, but the entire structure with the mirrors will experience a dip, a resonance dip. So the structure will have, the DBRs will make sure that you have reflection that has a certain bandwidth, and in this spectrum, this is also wavelength, you will have a resonance dip, and that dip is 1060 nanometers, roughly for us. So the difference between these, because when you add the mirrors to the gain, and you will get a lacing wavelength. So the resonance wavelength might be here, and the main peak is here. So the difference between these will be the detuning, which is 50 nanometers in my case. And when you start to bias the VCSEL, these peaks will move, and they move at different rates with temperatures. So when you bias the VCSEL, you will have a point where your current threshold is at the minimum. And when I measured OSA, my VCSELs, I found that the minimum threshold current was closer to 0 degrees, which indicates that the detuning was not as expected, I think. It should be, it shouldn't be that low. So there's room for optimization there, absolutely. That's why partly what I think is so exciting with my research is that this is the first iteration of 1060 nanometer VCSELs we've done at Chalmers, and they are the best in the world. So, and this is not an optimized, I mean, it is based on a truly great 850 nanometer design, but it's not, it hasn't been optimized further. So there's room for improvement, and I think that's really exciting.
Okay, thank you very much, Eva. And thank you also, and Stavros, for your questions. Do we have any more questions coming up here?
I have a comment, if I may say.
Yeah, I probably.
This that you say that the gain peak and the photoluminescence peak is about the same wavelength. That is not true, really.
It's related, kind of, I think.
Yeah, it's related, but the photoluminescence peak is on higher energies, so that's shorter wavelengths than the gain peak, and that's quite important. Yes.
So yeah, and that makes sense because it moves 3 times faster roughly than this. So if it was 1045, the detuning would be all weird. So there it is. So yes, so good comment. So this is actually, yeah, this peak is still here, but it's then lower than the PO peak.
Exactly.
Thank you, Rika. I know they're related, but you should have asked me how, and I wouldn't have been able to answer.
Okay. I see no further questions on the chat line here, so if there are no more questions, I think we would like to thank everyone who participated here, especially our faculty opponent and our grading committee who did great work here. And also for you out there in the cyberspace, staying with us this far and managing to uplink you 3 times on different links here. So thank you very much. Now what will happen is that we will have the grading committee and the opponent and also the supervisor to have a separate meeting. We will keep the YouTube link open so you can follow what happens afterwards here. It will be muted, but once we get back again, we will open up and you will be able to see what the verdict will be from the grading committee. And with that, thank you, Eva.
Thank you, Dag.
And thank you also, Henrik, for
I made a slide.
Arranging all these things. I think the technology failures were out of our control. I think it will depend on any VCSEL in the world. And maybe in the future we will see much better connections with the new VCSELs coming from Chalmers, I'm pretty sure. So with that, let me close this session. Thank you very much.
Thank you.
So maybe the chair could tell the decision here. So I think now we're back. We are all back here now, so we're eager to listen to the verdict.
Do you want the YouTube channel up for this?
The YouTube channel is up for this. Now it's streamed across the whole world. So I hope you stay with the decision you just told me.
I hope she won't cry.
Yeah.
No. So Lena, maybe you as the chair should convey the message.
Okay, I was selected to be chair of the committee, so it's my pleasure to pass the result to you, Eva. So anonymously you were you have passed the exam.
Yay!
So congratulations.
Thank you so much. I cannot hear myself.
So with that, we'd like to thank you all for helping out with this dissertation, and I think there's nothing else to it more than weekend coming up. So I wish you a good weekend here, and thanks for all your help. And
yes.
We will see the decision coming both digitally and in paper format eventually. So thank you very much. Henrik, Anders, vad gör vi härnäst?
Now I think there is something in the lunchroom.
Yes.
Yep, for.
Okay. Can we bring the streaming up to the?
No, we cannot do that. So we will close everything now.
So
thank you very
cheers, Eva. Cheers.
Thank you so much. And I really, you've been an awesome committee and opponent. I enjoyed your questions. They were all very relevant. So thank you.
Yeah, thank you very much, everyone.
Congratulations.
Thank you.
Thank you. Bye-bye.
Bye now.
Congratulations, and relax now, Eva.
Yay.
Okay, so let's do this one.
Exactly.
Congratulations.
Thank you. Oh. Thank you. Awesome. Handshakes.
Ja, jag kan hålla nästan ännu.
Inte riktigt än. Nu är allt nästan.